Two separate teams spent years measuring how fast the universe is expanding. They used different instruments, different methods, different parts of the sky. When the results came in, they disagreed by enough to break something. We are talking 5 sigma, the threshold physicists use to declare a genuine discovery. Except here, the discovery is that our entire model of the cosmos has a crack in it. And the expansion rate is just the beginning. There are strange alignments in the oldest light in existence. Galaxies that formed too early, too fast, too massive. A universe less clumpy than physics says it should be. If you enjoy what we do here, subscribe and hit the bell, because what we are about to find goes much deeper than anyone expected. There is a version of science where everything fits together perfectly. The equations describe reality precisely. Observations confirm those equations exactly, and the enterprise moves forward with clean confidence. For most of the 20th century, cosmology looked like that kind of science. The Big Bang model predicted that a faint glow of microwave radiation should fill the entire sky, a relic of the universe's earliest moments preserved in the cooling temperatures of expanding space, and when astronomers searched for it, the glow was exactly there, at exactly the predicted temperature, distributed across the sky in exactly the predicted pattern. The model predicted precise ratios of hydrogen, helium, and lighter elements forged in the first few minutes of cosmic existence, and when measurements were made in the oldest stars, the numbers matched with striking accuracy. It predicted that galaxies should not distribute themselves randomly through space, but should assemble along an intricate web of filaments and sheets surrounding vast empty voids. And when three-dimensional surveys mapped hundreds of millions of galaxies, the cosmic web was exactly where the equations said it would be. The standard cosmological model, known as lambda CDM, became the most comprehensive and successfully predictive description of the large-scale universe ever constructed by human science. Physicists working in the 1990s and early 2000s spoke of a golden era of cosmology, a period when the basic parameters of the cosmos were being measured with unprecedented precision and the standard model was being confirmed at every turn. And then the precision became too sharp and the problems hiding underneath it began to surface. The discomfort arrived in pieces, a small discrepancy here, a subtle statistical tension there, an anomalous pattern in one survey that might dissolve with more data. Scientists are rightly skeptical of isolated anomalies because the history of science is full of signals that looked significant and then disappeared under closer scrutiny. The early cracks in the standard model were noted and monitored and set aside with the expectation that improvements in measurement would resolve them. That expectation has proven wrong in a way that the field can no longer deny. The anomalies have survived increasingly precise measurements. Several have become more significant over time rather than less, and they now come from enough independent directions, enough different instruments, different methods, different phenomena probed at different scales, that the combined message is impossible to attribute to bad luck or systematic error in a single experiment. The story ahead is not a story of scientific failure. Lambda CDM is still the best map of the cosmos we have, and it is an extraordinary map, but maps can get the broad strokes right while failing at the specific features that matter most in specific situations. The universe has been writing corrections in the margins of the standard model for decades. The corrections have become too prominent and too consistent to set aside any longer. At the center of the story is a deceptively simple number. The Hubble constant describes how fast the universe is expanding. Specifically, how much faster each galaxy recedes from us for every additional unit of distance between us and it. Edwin Hubble discovered in the 1920s that distant galaxies are moving away from us in all directions, leading to the understanding that space itself is expanding outward from every point simultaneously. Measuring the precise rate of this expansion became one of cosmology's central obsessions for the rest of the 20th century. The uncertainty was genuinely embarrassing. Different groups of astronomers could not agree on the Hubble constant to within a factor of 2 for decades. and that uncertainty infected every calculation that depended on it: the age of the universe, the scale of the observable cosmos, the rate of structure formation, the timeline of everything that has ever happened. By the early 2000s, precision instruments finally brought the uncertainty down to manageable levels. The field converged on a value near 70 kilometers per second for every 3 million light-years of distance, and the sense was that the basic framework was established. The remaining uncertainty would shrink further with time, and the number would settle. This situation is genuinely unusual in the history of quantitative science. Most scientific crises involve one measurement disagreeing with one prediction. The Hubble tension involves two highly precise, thoroughly audited measurement campaigns, using completely different physical principles and completely different observations. Both are internally consistent, both have been verified by multiple independent groups, and both produce the wrong answer relative to each other. Fixing it requires adding new physics to the model, and every proposed addition carries its own complications. What is being tested here is the accuracy of two numbers. More fundamentally, it is the entire theoretical framework that connects the early universe to the late one. What settled instead was a 5 sigma discrepancy between two different ways of measuring the same constant. How you measure the expansion rate determines what you find, and the universe's two most precise answers disagree in a way that is statistically impossible to dismiss. This is the Hubble tension, and it sits at the center of the deepest crisis cosmology has faced since the discovery of dark energy itself. The cosmic microwave background is the oldest light we can see. It was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the young cosmos was an opaque, glowing plasma. Photons could not travel freely because they were continuously scattered by the dense sea of charged particles they moved through. The universe was sealed shut to light. Then, over a brief span of time, as temperatures dropped below roughly 3,000 degrees, neutral atoms formed throughout the cosmos simultaneously. The plasma cleared. Light that had been locked inside the dense fog poured outward in all directions. Beginning a process it has continued for nearly 14 billion years, stretched by cosmic expansion to longer wavelengths. Cooled by the vast distances traveled, those photons reach our detectors today as a delicate hiss of microwave radiation at a temperature of 2.7 degrees above absolute zero. The background is not a featureless uniform glow. Mapped with sufficient sensitivity, it reveals an intricate texture of temperature fluctuations, hot spots, and cold spots that differ from the average by about 1 part in 100,000. These fluctuations are the imprints of quantum fluctuations from the very first moments of existence, amplified by inflation to macroscopic scales, and then further shaped by the physics of the early plasma. They carry an almost unbelievable amount of information compressed into these tiny temperature variations. The Planck satellite mapped this background with the finest angular resolution and sensitivity ever achieved, operating from 2009 to 2013. The analysis team extracted precise values for every major cosmological parameter by studying the statistical properties of the temperature variations, specifically the angular scales at which hot and cold patches cluster most prominently. The physics behind this extraction rests on acoustic oscillations in the early plasma, pressure waves moving through the hot, dense, ionized gas at roughly half the speed of light, establishing a preferred scale that corresponds to the maximum distance such a wave could travel before the plasma froze at recombination. Measuring the apparent angular size of that scale on the sky, combined with the calculated physical size of the sound horizon, precisely determines the expansion history and current expansion rate. The Planck team's result, the Hubble constant today, should be 67.4 kilometers per second for every 3 million light-years of distance, with an uncertainty of less than 0.5%. This is not merely a measurement of the early universe. It is a prediction, a specific statement about what any independent measurement of the universe's current expansion rate should find if the Standard Model correctly describes the evolution from 380,000 years after the Big Bang to the present day. Verify the prediction against independent measurements, and you have tested the model. Fail to verify it, and something in the model is wrong. The Planck satellite's measurement represents one of the most sophisticated observational campaigns in the history of astronomy. The instrument operated at multiple frequencies simultaneously, allowing researchers to separate the cosmological signal from the microwave emission of the Milky Way and other foreground sources. The temperature fluctuations it measured were smaller than the thermal noise of the detectors, requiring years of careful calibration and systematic error characterization. The resulting cosmological parameter extraction involved multiple independent analysis teams, using different statistical methods, all arriving at consistent answers. The Planck result is not a quick calculation. It is the product of an entire generation of precision measurement science. The prediction fails. The independent measurements return a substantially higher number, and both the prediction and the independent measurements have been verified to within 1% uncertainty. The Standard Model connecting the ancient universe to the present one is producing two contradictory answers about the same physical universe. That contradiction is one of the most important unsolved problems in contemporary physics, and every major cosmological survey of the coming decade will dedicate significant effort to understanding it. The second way to measure the universe's expansion rate builds a chain of calibrated distance measurements, rung by rung, out into the present-day cosmos. The approach is elegant in principle. Find objects whose intrinsic brightness is known through independent calibration. Compare that intrinsic brightness to how bright the object appears in the sky, and calculate distance from the ratio. Accumulate enough such measurements across a sufficient range of distances, and you can determine how fast space is expanding today with high precision. The result is called the cosmic distance ladder, and the care with which its rungs have been constructed and cross-checked represents some of the finest observational astronomy ever practiced. The first rung uses Cepheid variable stars. These are massive, pulsating stars that brighten and dim in a regular rhythm over periods ranging from a few days to a few weeks. The crucial property of Cepheids, discovered by Henrietta Swan Leavitt in 1908 through patient observation of variable stars in the Small Magellanic Cloud, is that their pulsation period is directly related to their intrinsic luminosity. Longer period Cepheids are intrinsically more luminous. Measure the period of the pulsation and you know the true brightness. Compare that to how bright the star appears in the sky and you have a reliable distance. This period luminosity relationship has made Cepheid stars the workhorses of extragalactic distance measurement for over a century. With Cepheids establishing reliable distances out to tens of millions of light years, the ladder extends its next rung to Type Ia supernovae. These are explosions of white dwarf stars, dead stellar remnants, that have accumulated enough mass to trigger a runaway thermonuclear chain reaction that completely destroys the star in an event so energetic that it briefly outshines its entire host galaxy. Because the mechanism triggering the explosion is physically constrained, these supernovae have a characteristic peak brightness that can be standardized with corrections for the rate at which the light fades. Type Ia supernovae, detected billions of light-years away, give access to a vast span of cosmic history. The SH0ES collaboration, under the leadership of Adam Rees, spent more than a decade assembling this ladder with extraordinary rigor, measuring hundreds of Cepheid stars in dozens of carefully selected galaxies that had also hosted measurable Type Ia supernovae, establishing each cross-calibration with multiple independent checks. Their best measured value for the Hubble constant, 73 kilometers per second for every 3 million light-years of distance, with an uncertainty just above 1%. Multiple late universe methods now confirm values above 70 for the Hubble constant, independent of the Cepheid and supernova distance ladder. Gravitational wave observations of merging neutron stars provide a distance measurement grounded in general relativity alone, with no photometric calibration involved. Time delays between multiply-imaged quasars lensed by foreground galaxies give yet another independent route through a completely different physical effect. All of these methods prefer a higher expansion rate than Planck predicted. The tension runs between an entire family of independent late universe methods and the Standard Model's early universe prediction, 73 against 67.4, an 8% gap. The statistical significance of this discrepancy is approximately 5 sigma, the same threshold used to announce the discovery of the Higgs boson, the detection of gravitational waves, and other landmark results in modern physics. The James Webb Space Telescope checked the Cepheid measurements by resolving individual stars in crowded fields that earlier instruments had blurred together, testing whether stellar crowding had biased the distances upward. It found a real crowding effect, and found it far smaller than needed to close the gap. The tension at 5 sigma remains. The universe is giving two different answers about how fast it is expanding, and both answers have been verified independently to within 1%. Empty space is not empty. This conclusion, arrived at through the mathematics of quantum mechanics, is one of the stranger gifts theoretical physics has given us, and the universe has taken it and done something with it that physics cannot explain. Quantum mechanics requires that even a perfect vacuum be filled with ceaseless activity. The uncertainty principle prevents any quantum field from settling into a state of absolute zero energy. Instead, virtual particles, paired combinations of a particle and its antiparticle, constantly flicker into existence at the limits of what uncertainty permits, exist for intervals so brief they cannot be directly observed, and then annihilate each other back into nothingness. This activity is real. The Casimir effect provides direct experimental confirmation. Two uncharged metal plates placed extremely close together experience an attractive force because the constraints the plates impose on vacuum fluctuations between them create an energy imbalance that pushes the plates together. Empty space pushes back. It has energy. The cosmological constant problem arises when you try to calculate how much energy. Add up the contributions from every particle type in the Standard Model of physics, including every quantum field fluctuating in the vacuum, up to the energy scale at which physicists expect both quantum mechanics and general relativity to be simultaneously relevant. The result is a vacuum energy density approximately 10 to the power of 120 times larger than the cosmological constant. We actually observe driving cosmic acceleration. Written out in full, this comparison looks like the theoretical prediction is 1 followed by 120 zeros times larger than reality. No other measurement in the history of science has produced a theoretical prediction that fails by this margin. The cosmological constant problem is not a precision issue or a frontier effect at the edge of knowledge. It is a catastrophic mismatch between the two most successful theories in physics, quantum mechanics, and general relativity when they are asked to predict the same observable quantity. The cosmological constant problem has a historical dimension worth acknowledging. For decades after the discrepancy between the quantum prediction and the observed value became clear, the cosmological community essentially decided to ignore it. The Standard Model worked well enough at the scales being probed, and the constant could be treated as a free parameter to be set by observation. The discovery of dark energy in 1998 changed this. Suddenly, the cosmological constant had a measured value, and that value needed to be explained rather than simply accepted. The vacuum energy problem went from being an embarrassment at the edges of theoretical physics to being a central unsolved problem sitting at the heart of the most successful cosmological framework ever built. If the vacuum energy actually had its theoretically predicted value, space would curve so violently that atoms, molecules, planets, stars, galaxies, and every structure we observe would be impossible. The universe, as we observe it, requires a cosmological constant that is approximately 10 to the 120, smaller than the raw calculation gives. No physical mechanism has been identified that makes it this small. No symmetry principle demands this particular value. Every proposed resolution, fine-tuning, supersymmetric cancellation, anthropic selection across a landscape of possible vacuum energies carries significant theoretical problems and no experimental support. The universe accelerates, dark energy exists, and the value of dark energy's density is a number that breaks physics. For 25 years after two independent teams discovered cosmic acceleration in 1998, cosmologists treated dark energy as a cosmological constant, a fixed, unchanging energy density belonging to empty space itself. The lambda in lambda CDM is this constant, and it was placed in the model as the simplest possible explanation for the observations. Simplicity in physics carries weight. When observations can be explained with fewer assumptions, you should prefer fewer assumptions until the data demand more. And for 2.5 decades, observations were consistent with a constant. But consistent with a constant is a weak statement. A constant dark energy and a slowly evolving dark energy produce nearly identical observational signatures across the range of cosmic history that older surveys could probe. Telling them apart requires precise measurements of the universe's expansion across many different epochs, catching any drift in the dark energy density as the universe aged. That kind of precision requires a very specific kind of instrument. The Dark Energy Spectroscopic Instrument, mounted on a 4-meter telescope at Kitt Peak Observatory in Arizona, was designed and built for this purpose. 5,000 robotic fiber positioners sit in its focal plane, each capable of being independently aimed at a different galaxy or quasar target and redirecting that object's light into a spectrograph. The instrument observes 5,000 targets simultaneously, recording precise distances and velocities for each. Over its survey, DESI has built a 3-dimensional map of the universe containing tens of millions of objects spanning roughly 11 billion years of cosmic history, the most complete such map ever assembled. The key signal DESI extracts is baryon acoustic oscillations, the same primordial sound waves that left characteristic scales in the microwave background also left them in the clustering pattern of galaxies. There is a preferred separation scale of roughly 490 million light-years, visible in how galaxies cluster relative to each other, corresponding to the distance those primordial sound waves traveled before the early plasma froze. This scale acts as a standard ruler, measuring how its apparent size changes as you look at different cosmic distances, reconstructs the expansion and geometry of the universe at each epoch. In 2024, DESI released results from its first major data collection. The data prefer a dark energy that is not quite constant. The specific signature appears in the equation of state parameters, numbers that characterize how dark energy's density changes as the universe expands. A true cosmological constant has fixed values for these parameters. DESI's data are better fit by values suggesting dark energy was somewhat stronger in the recent cosmic past and appears to be weakening. The statistical significance sits around 2.5 sigma, below the 5 sigma discovery threshold, but directionally consistent across multiple independent analyses. Other datasets from weak lensing surveys and supernova compilations have found hints pointing in the same direction. The DESI results gain additional weight when placed alongside other independent analyses pointing in the same direction. The Pantheon Plus supernova dataset, analyzed with updated photometry and a larger sample, finds mild preferences for dark energy evolution. Some weak gravitational lensing analyses also prefer cosmological parameters consistent with slowly evolving dark energy. No single hint from any of these datasets reaches high significance on its own, but when independent instruments probing different physics at different scales consistently find the same directional signal, the combined weight of evidence is greater than any individual result alone. The DESI 2.5 sigma signal is the most precise measurement in this direction, but it did not arrive in isolation. If dark energy is truly evolving, the universe's future is no longer a settled question. A cosmological constant leads to one specific fate: eternal accelerating expansion, each galaxy receding beyond every other galaxy's horizon, all stars eventually dying, the cosmos growing cold and empty across incomprehensible spans of time. A dynamical dark energy field has a future that depends entirely on how that field evolves. It could weaken and allow gravity to decelerate and eventually reverse expansion. It could strengthen and tear apart every structure in the cosmos. The universe's ending, which we thought we understood, may be the piece of the picture we have been most wrong about. There is a scar on the oldest photograph of the universe. It sits in the southern sky, occupying a region roughly 30 times the apparent width of a full moon, and it is measurably colder than the surrounding microwave background. The background itself is covered in temperature variations. That is expected and understood, but statistical analysis of the full Planck sky map consistently finds that a cold region, this large and this cold, should appear by chance, less than 1% of the time in a universe governed by the Standard Model. Some analyses place the probability significantly below that threshold. The cold spot was first identified in data from the WMAP satellite and later confirmed at higher resolution and sensitivity by Planck. Multiple independent teams using different analysis techniques have verified its anomalous character. It has not dissolved under scrutiny. It persists. The most physically motivated explanation is a supervoid, an enormous, underdense region of space located between us and the background radiation through which the ancient photons passed on their long process to our detectors. When microwave background photons travel through an underdense region in a universe where dark energy is driving expansion, they lose a small amount of energy through the integrated Sachs-Wolf effect. Entering the void, a photon gains a little energy by falling toward the void's gravitational center. Exiting the void, it must climb back out of that gravitational well. In an accelerating universe, dark energy has expanded the void during the photon's transit, making the exit slope slightly steeper than the entrance slope. The photon emerges with marginally less energy than it entered with. Across a void spanning 1 billion or more light years, the accumulated energy loss creates a cold imprint. When astronomers searched for the supervoid, they found one, a genuine underdensity in the right direction at roughly the right distance of about 1.5 billion light years. But the quantitative match remains contested. Whether the observed void is physically large enough and sufficiently empty to fully explain the cold spot's depth has been actively debated without resolution. Some analyses find the numbers work out. Others find a significant shortfall that requires an additional explanation beyond a supervoid alone. Understanding the integrated Sachs-Wolf effect is essential for appreciating why the cold spot is difficult to explain. Away. In a universe without dark energy, potential wells created by matter overdensities would be static. A photon entering an overdensity would gain energy descending into the potential well and lose exactly the same energy climbing back out, for a net effect of 0. Dark energy changes this calculation by causing potential wells to decay as they expand. Photons entering a decaying well gain energy on the way in and lose less energy on the way out, ending with a small net gain. For underdense regions, the logic reverses. Photons traveling through voids lose a small net amount of energy. The cold spot, if caused by a supervoid, is the integrated Sachs-Wolf effect operating over a void spanning more than 1 billion light years. The alternative proposals that have not been ruled out include cosmic textures, topological defects left over from symmetry breaking in the earliest moments of the universe, and the genuinely extraordinary possibility of a bubble collision, the imprint of our universe having collided with a neighboring bubble in an inflationary multiverse. Both remain speculative. The cold spot sits in the southern sky, colder than expected, with no definitively established cause after decades of investigation. The cold spot is one specific anomaly in one specific region of the sky. What comes next is not one anomaly but an alignment, a preferred direction that appears in the large-scale structure of the microwave background itself, attacking the most fundamental assumption in all of cosmology. The cosmological principle is the architectural load-bearing wall of the entire Standard Model. It states that the universe is isotropic, statistically the same in all directions, and homogeneous, statistically the same at every location. Without this principle, the equations describing cosmic expansion cannot be globally applied. The Hubble constant would not be a single universal number, but could vary with direction. Distances inferred from redshifts would depend on which direction you look. The microwave background would need to be interpreted as a signal from an anisotropic universe rather than a statistically isotropic one. Every major tool of cosmological analysis would need fundamental revision. In the years following the launch of the WMAP satellite, researchers examined the two largest scale patterns in the microwave background's temperature map. These are the quadrupole and octopole modes, temperature variations that stretch across the entire sky rather than localized regions. In a truly isotropic universe with random initial conditions, the orientation of these two patterns should be statistically independent of each other and independent of any physical structures in our cosmic neighborhood. They are not independent. The planes of the quadrupole and octopole are closely aligned with each other, and that alignment also roughly coincides with the plane of Earth's orbit around the star at the center of our solar system and with the celestial equator. These are purely human-defined coordinate systems. The microwave background, stamped with information about the universe at 380,000 years old, cannot know about the orbital plane of the planets. The probability of this specific alignment arising by random chance under the Standard Model is less than 1%. Researchers who discovered it named it the axis of evil, a deliberately provocative label pointing to how wrong the alignment seems in a universe that should have no preferred direction. The axis of evil has stimulated research into whether the universe might have a non-trivial topology, a shape that wraps around on itself in specific ways. If the universe is finite and small enough for its boundaries to be visible within our observable horizon, the largest scale patterns in the microwave background would show specific correlations. Matched circles of identical temperature pattern appearing in pairs on opposite sides of the sky, like the way a finite room would show your own back to you if you looked far enough ahead. Searches for these circles in Planck data have not found them at the scales where they would most easily be visible, but they have not ruled out all possible topologies. A universe with a specific large-scale topology could naturally produce preferred directions without violating any local physical principle. The axis of evil survived the Planck satellite's more precise measurements. More than 20 years of analysis, using different foreground cleaning approaches and different statistical frameworks, have not explained it away as a measurement artifact. It remains either a genuine large-scale asymmetry in the cosmos or a systematic effect that has successfully hidden from every method of detection attempted. If it is real structure in the universe, the cosmological principle is violated at the largest scales we can observe. The axis of evil lives in the 380,000-year-old microwave background. The same preferred direction appears independently in the distribution of the most distant objects observable in today's universe. Finding identical directional signals in two completely unconnected datasets is not something statistics can easily dismiss, and the second signal is at 5 sigma. The microwave background has a large-scale temperature asymmetry, called the dipole. One hemisphere of the sky looks slightly warmer, the opposite hemisphere slightly cooler. This is the Doppler effect of our motion through space, the cumulative velocity of our solar system moving within the Milky Way, the galaxy moving within its local group, and the local group being gravitationally attracted toward nearby massive concentrations of matter, all add up to a net motion of roughly 370 kilometers per second in a specific direction. The resulting temperature shift is well understood and predictable, and the direction has been precisely measured by the Planck satellite. This motion makes a testable prediction about the distribution of very distant astronomical objects. If we are genuinely moving in a specific direction through space, the density of objects should be slightly higher in the direction of motion. We are moving toward those objects, so they appear slightly more concentrated per patch of sky and slightly lower in the opposite direction. This number count dipole in the distribution of radio galaxies and quasars should have a predictable amplitude and direction set by the measured CMB velocity. Multiple surveys have now measured this effect. In every case, the measured dipole in the distribution of distant radio sources and quasars is substantially larger than what the CMB kinematic velocity alone predicts. A comprehensive 2022 analysis using over 1 million quasars found the excess at approximately 5 sigma significance. Independent analyses using different radio galaxy catalogs find consistent directional signals with similar statistical strength. The explanations for this excess are limited. Either our total peculiar velocity through space is significantly larger than the CMB dipole measurement implies, requiring a massive hidden concentration of matter, accelerating our entire cosmic neighborhood without any clear gravitational signature in the local galaxy distribution, or the universe has a real, physical preferred direction built into its large-scale structure at scales far beyond our local environment. A genuine cosmological anisotropy would mean the universe is not the same in all directions when examined at the scales of billions of light-years, precisely where the standard model most requires it to be. The cosmological implications of a confirmed large-scale anisotropy extend far beyond the microwave background. Anisotropic expansion would affect how we interpret the redshift distance relation for galaxies. When we measure the redshift of a distant galaxy and convert it to a distance using the standard Hubble constant, we assume the universe expands at the same rate in all directions. If the expansion rate varies with direction, the inferred distances to objects in different parts of the sky would be systematically off in a direction-dependent pattern. The entire distance scale that cosmologists use to measure dark energy, the age of the universe, and the large-scale geometry of space would need to be corrected for the anisotropy before meaningful results could be extracted. 3 independent anomalies: the axis of evil in the background radiation, the cold spot in the southern sky, and the dipole excess in distant radio sources are all pointing in the same general direction. That is the kind of coincidence that demands explanation. In 1975, Vera Rubin and Kent Ford published a paper about the rotation of stars in spiral galaxies that would eventually overturn one of the most basic assumptions about what the universe is made of. Their work was not controversial in the way revolutionary ideas are sometimes received with immediate hostility. It was more quietly devastating, a dataset so careful and so consistent that it left no room for disagreement about what it showed, only about what it meant. The setup was straightforward. Astronomers have understood since Newton that objects orbiting a central mass should move at speeds that depend on how much mass lies interior to their orbits. Planets close to a massive central star orbit fast. Planets far from it orbit slowly. The outer planets of our own solar system creep around their paths at a small fraction of the speed of the inner ones. This relationship between orbital speed and distance from the central mass is a direct consequence of gravity, and it should apply equally well to stars orbiting within a galaxy. Stars far from the galactic center, where most of the luminous mass is concentrated in the bright central bulge, should orbit more slowly than stars close in. The rotation velocity should fall off with distance from the center, forming what astronomers call a Keplerian decline. Rubin and Ford measured the rotation velocities of stars at different distances from the centers of several spiral galaxies, expecting to confirm this decline. What they found instead was that the velocity curves were flat. Stars in the outer arms of galaxies were orbiting at essentially the same speed as stars near the bright, dense center, not slightly slower, not marginally slower, but essentially the same. And the flat rotation curves extended outward to the very edges of the detectable stellar disk with no sign of dropping off. A star orbiting at those speeds, that far from the galactic center, with only the visible matter to hold it in, would escape. The visible mass of a galaxy is insufficient by a large factor to keep outer stars gravitationally bound at the speeds that are observed. Something else, must be providing the gravitational force. That something must be massive. It must extend well beyond the visible disk in a roughly spherical halo, and it must be invisible at every wavelength then available. Rubin and Ford had found the most direct observational evidence for what would become one of the dominant concepts in modern cosmology: dark matter. The dark matter framework that emerged from flat rotation curves in the 1970s gained support from multiple independent directions in the years that followed. Gravitational lensing, the bending of light by mass, provided a completely independent way to measure the total mass of galaxies and clusters, and the lensing inferred masses consistently exceeded the visible mass. The statistical properties of galaxy clustering in large surveys could only be reproduced in models that included cold, dark matter. The temperature fluctuations in the cosmic microwave background were precisely predicted by models with dark matter and failed completely without it. Dark matter became a prediction confirmed by completely different methods in completely different contexts, cementing its central role in the standard cosmological model. The decades that followed produced both extraordinary theoretical success and stubborn observational failures, and understanding both is essential to understanding why the dark matter story is more complicated than the textbooks initially suggested. Cold dark matter, particles that were moving slowly at the time of their formation, interacting only through gravity and possibly the weak nuclear force, predicts the large-scale structure of the universe with remarkable accuracy. Cosmological simulations using cold dark matter produce cosmic webs of galaxies, filaments, and voids that match observations at scales of hundreds of millions of light-years and above. The microwave background power spectrum, the baryon acoustic oscillation scale, the galaxy clustering statistics from massive surveys, all are well described by models where the dark matter is cold and collisionless. But zoom in from the cosmic scale to the scale of individual galaxies, and the predictions start disagreeing with observations in specific, repeatable ways. Each failure mode has a name, and the names together read like an indictment of the simple cold dark matter picture. The core cusp problem is the first. When you simulate the formation of a galaxy-sized dark matter halo from scratch, using cold dark matter, the resulting density profile has a characteristic shape. The density of dark matter rises steeply as you move toward the center of the halo. This is a mathematical cusp. The density increases sharply without leveling off, becoming progressively more concentrated toward the core. Every high-resolution cosmological simulation, regardless of the specific code or research group that runs it, produces this cuspy inner profile. The prediction is robust and consistent. When astronomers measure the actual dark matter distribution inside real dwarf galaxies, small, low-luminosity systems, where dark matter dominates the gravitational budget and the contaminating effects of stellar mass on the kinematics, are relatively small, they systematically find something different. The dark matter in real dwarf galaxies has a flat chord density distribution in the center. The density does not spike steeply inward. It levels off into a region of roughly uniform density that can span several hundred light-years across. Cusps are predicted. Cores are consistently observed. This discrepancy is not a marginal statistical effect. Cores and cusps are qualitatively distinct forms for a density profile requiring different physics to produce. Studies of the best observed dwarf galaxies, using stellar kinematics and other techniques to infer the underlying mass distributions, find chord profiles in a significant fraction of them. The challenge to the cold, dark matter prediction is systematic and has persisted for more than 2 decades of increasingly precise observations. One of the most important tests of the core cusp problem comes from isolated dwarf, irregular galaxies, small galaxies with ongoing but not vigorous star formation that are not satellites of larger systems. For these galaxies, tidal interactions with a host galaxy cannot have altered the dark matter distribution, and the star formation history is gentle enough that extreme supernova feedback is unlikely to have driven dramatic gas outflows. When the dark matter density profiles of these isolated field dwarfs are measured, they still show chord distributions. The baryonic feedback explanation for core creation requires significant star formation, specifically concentrated at the center of the galaxy, to generate the gas outflows that transform cusps into cores. In systems where this kind of star formation clearly did not occur, the chord profiles that should not be there according to cold dark matter are still there. The proposed resolution within the cold dark matter framework invokes the feedback of visible matter. When massive stars form in a galaxy's central region, they eventually explode as supernovae, releasing enormous amounts of energy and driving rapid outflows of gas. As gas is suddenly expelled from the center of a galaxy, its gravitational influence on the surrounding dark matter changes abruptly. The dark matter responds by expanding outward slightly, and over multiple cycles of star formation and gas expulsion, a cuspy dark matter profile can theoretically be transformed into a chord one. This baryonic feedback mechanism is physically motivated and has support from some simulations, but it requires specific conditions: the right amount of star formation concentrated at the right mass scale with the right timing of feedback events, and it struggles to explain chord profiles in dwarf galaxies with too few stars to have driven the necessary gas outflows. The missing satellites problem strikes at a different scale. Cold dark matter simulations of Milky Way-sized galaxies produce a central galaxy plus an entourage, hundreds to potentially thousands of smaller dark matter subhalos orbiting the central galaxy, each one a potential host for a satellite dwarf galaxy. The hierarchical nature of structure formation in cold dark matter leads naturally to this prediction. Large halos are built up from smaller ones, and the remnants of that assembly process leave behind a rich swarm of satellite substructure. Astronomical surveys of the Milky Way's satellite population have found far fewer. For most of modern astronomical history, only about a dozen classical dwarf galaxy companions were known. Deeper surveys using digital sky databases sensitive to extremely faint and diffuse stellar systems have expanded the count significantly, discovering several dozen ultra-faint dwarfs that escaped earlier detection due to their extremely low surface brightnesses. The most optimistic current census, accounting for survey incompleteness corrections, reaches somewhere between 50 and perhaps 100 confirmed or suspected satellite galaxies. Cold, dark matter simulations routinely predict several hundred to more than 1,000 subhalos capable of hosting visible galaxies around a Milky Way-sized host. The shortfall is real and substantial. One explanation that preserves cold, dark matter invokes the ultraviolet radiation produced by the first stars and quasars after the cosmic dark ages ended. This reionization process, occurring roughly 600 million years after the Big Bang, flooded the universe with energetic photons that heated and evaporated the gas inside small dark matter halos before stars had time to form, leaving behind dark, invisible substructure that orbits the Milky Way without any associated stellar population. If most of the predicted subhalos are genuinely dark, stripped of any stars by reionization, the satellite galaxy count would be much lower than the total subhalo count. The future satellite census of the Milky Way is one of the most concrete predictions of the dark matter model, with a specific timeline for resolution. The Vera Rubin Observatory's LSST survey began science operations in 2025 and will cover the entire southern sky to depths far below any previous survey. Within a few years of operations, it will have found essentially every satellite galaxy brighter than a few hundred solar luminosities within several 100,000 light-years of the Milky Way. If dark matter's prediction of hundreds of luminous satellites is correct, LSST will find them. If the prediction fails, it will fail in an inescapable and statistically robust way, with an instrument designed specifically to eliminate the completeness arguments that have kept the problem open. The missing satellites problem is approaching its definitive test. The explanation has quantitative limits. Not all missing satellites can be attributed to reionization. The halos most affected are the smallest ones, and the shortfall extends into mass ranges where reionization should not be fully effective. The Legacy Survey of Space and Time, operating with the Vera Rubin Observatory, will detect satellite galaxies to depths far beyond previous surveys. Its results will either confirm that the missing satellites are simply too faint to have been seen before, or establish definitively that the prediction overestimates the satellite population at a level the model cannot accommodate. The too big to fail problem is the most conceptually direct challenge of the three. Cold, dark matter simulations of Milky Way-sized galaxies predict several massive, dense ones, dark matter structures with such deep gravitational wells that the processes invoked to suppress star formation in smaller halos simply cannot work here. These massive subhalos are too large for reionization to evaporate their gas. They are too large for stellar feedback to disrupt their structure. They are, in the language of the problem, too big to have failed to form bright, easily detectable galaxies. Yet when astronomers examine the real satellite galaxies of the Milky Way and measure their internal kinematics, the observed satellites systematically have less concentrated dark matter in their interiors than the most massive predicted subhalos. The dense, compact subhalos that simulations place in the top of the mass distribution around the Milky Way simply do not correspond to any observed satellite. The prediction is for easily detectable, dense systems. The observations find only diffuse, lower mass systems in that part of the subhalo mass function. Proposed resolutions again involve improvements to the feedback physics in the simulations. Perhaps interactions with the Milky Way's disk tidally stripped some of the densest subhalos, or perhaps stellar winds and radiation were unusually efficient at redistributing dark matter in this specific mass range. These arguments require careful tuning and rely on feedback processes still uncertain in the simulations. The problem has been known for more than a decade without a resolution that satisfies the full range of observers who have studied it. The too big to fail problem has a version that applies to galaxies throughout the universe. When the internal velocity dispersions of dwarf galaxies in different environments are measured and used to infer the masses and central densities of their dark matter halos, a pattern emerges. The most massive predicted subhalos are consistently absent from the observed catalogues of satellite galaxies around Andromeda and in the environments of field galaxies surveyed in cosmological studies. The problem is not a local quirk of our specific galactic neighborhood. It is a systematic feature of the comparison between cold, dark matter simulations and observations of small-scale structure wherever that comparison has been made carefully. Together, the Caucus problem, the missing satellites problem, and the too big to fail problem form a cluster of specific, related failures of cold, dark matter predictions at the scale of individual galaxies and their satellite populations. The contrast with cold, dark matter's large-scale successes is sharp, and it has driven 2 decades of intensive work on both observational and theoretical fronts without reaching consensus. In 1983, Mordechai Milgram proposed a modification to Newton's law of gravity that applies specifically in regimes of very low gravitational acceleration. His framework, MOND, predicts that below a specific critical acceleration threshold of about 1.2 times 10 to the negative 10 meters per second squared, far below anything encountered in the solar system or in any laboratory experiment, the effective gravitational force falls off more slowly with distance than the standard inverse square law. At high accelerations, the modification is negligible and standard gravity is recovered exactly. At the low accelerations found at the outer edges of rotating galaxies, the modified force is much stronger than standard gravity would give, producing flat rotation curves without any dark matter at all. The success of MOND at predicting galaxy rotation curves is not a loose qualitative match. Given only the observed distribution of a galaxy's visible matter, MOND predicts the full shape and amplitude of the rotation curve with precision and consistency across hundreds of galaxies spanning a wide range of masses, sizes, and surface brightnesses. The prediction works for high surface brightness spirals, low surface brightness dwarf spirals, and extremely faint dwarf irregulars. The scatter around the MOND prediction is remarkably small. Even more striking is MOND's prediction of the baryonic Tully-Fisher relation, the tight correlation between a galaxy's total visible mass and its maximum rotation velocity. This relation is observed to have very little scatter around a specific power law. MOND predicts this relation exactly as a direct algebraic consequence of the modified force law. Cold dark matter models struggle with this prediction because in those models, the dark matter halo contribution to rotation velocity is not uniquely determined by the visible mass. Different halo assembly histories can produce different rotation velocities for the same visible mass, generating scatter that the data does not show. MOND's failures are equally important to understand. The model breaks down at the scale of galaxy clusters. Within galaxy clusters, the visible mass, stars and hot gas, is insufficient even with MOND's enhanced gravity to explain the high velocities of the member galaxies, or the strong gravitational lensing of background objects that passes through the cluster. Some form of unseen mass is still required in clusters, even with MOND. The framework that eliminates the need for dark matter in individual galaxies cannot eliminate the need for something like dark matter at larger scales. The debate between modified gravity and dark matter has continued to generate new observational tests. One of the most powerful has been the bullet cluster, a system of two galaxy clusters that recently collided. The hot gas in the clusters, which interacts electromagnetically, has been slowed by the collision and sits between the two cluster cores. The dark matter and galaxies, which are nearly collisionless, have passed through each other. Gravitational lensing maps of the total mass distribution show the mass peaks offset from the hot gas and coinciding with the galaxy concentrations, exactly where dark matter particles would be after passing through each other without interacting. This spatial separation between the observed gas and the gravitational mass is very difficult to explain with modified gravity, which ties the gravitational force directly to the distribution of baryons. The bullet cluster is often cited as the strongest single piece of evidence for particle dark matter. The deeper problem is the absence of a complete relativistic theory. MOND, in its original form, cannot make predictions about the microwave background or large-scale structure because those phenomena require general relativity extended to cosmic scales. Attempts to build a relativistic version of MOND, most notably TVs, have faced serious constraints from gravitational wave observations. The measurement of gravitational waves from merging neutron stars by LIGO in 2017 established that gravitational waves travel at the speed of light to extraordinary precision. Several MOND-like relativistic frameworks predicted a different propagation speed, placing them in direct conflict with this result. The debate between modified gravity and dark matter remains live, but dark matter currently holds the dominant position. The S8 tension is less famous than the Hubble tension, but equally real, and the two anomalies together suggest that the standard model has systematic failures at multiple levels of the cosmic structure hierarchy. The parameter S8 is a combination of the matter density of the universe and the amplitude of density fluctuations, how strongly matter has clumped together on large angular scales. Together, these describe the total amount of structure that has grown over cosmic time under the influence of gravity. The Planck satellite's microwave background analysis provides a precise prediction for S8 today. Direct measurements of the late universe consistently find a lower value. The observational technique for the late universe S8 measurement is weak gravitational lensing. Light traveling from distant background galaxies is subtly deflected by the gravity of all the matter it passes through on the way to our telescopes, dark and ordinary matter alike. This deflection causes the background galaxies to appear slightly distorted in shape, stretched and sheared by amounts too small to detect in individual galaxies, but visible as a statistical signal in the correlated shape distortions of millions of them simultaneously. By mapping these shape correlations across large patches of sky, researchers reconstruct the distribution of all matter between us and the background galaxies. 3 major independent surveys have each measured S8 from different patches of sky with different telescope systems operated by different teams. The Kilodegree Survey in Europe, the Dark Energy Survey in the United States, and the Hyper-SuPrime-Cam program in Japan have all returned S8 values approximately 2 to 3 sigma below the prediction from the Planck microwave background analysis. The agreement among 3 independent datasets using 3 independent instruments is a strong indicator that the tension reflects a real physical discrepancy rather than a measurement artifact specific to any single experiment. The universe is less clumpy than the standard model says it should be. Something has suppressed the growth of large-scale structure relative to what gravity acting on the initial conditions defined by the microwave background should have produced. Proposed explanations include massive neutrinos, which free stream out of density fluctuations and suppress small-scale structure growth if their masses are near the upper end of current observational constraints. Dynamical dark energy that has been weakening over the recent cosmic past would reduce the rate at which gravity builds structure, lowering S8 from what a constant dark energy would predict. Some form of interaction between dark matter and dark energy, in which energy transfers between the 2 components alter both the expansion history and the structure growth rate, can reduce both the Hubble tension and the S8 tension simultaneously in specific regions of parameter space, though no such model has been confirmed. The connection between S8 and the growth rate of cosmic structure provides a direct observational test that complements the lensing measurement. The growth rate can be independently measured from the peculiar velocities of galaxies, specifically from how strongly galaxies cluster in a way that depends on whether the clustering is radially symmetric or shows a distortion along the line of sight because of infalling motions. This technique, called redshift space distortion analysis, measures a combination of the matter density and the logarithmic growth rate of structure, called F sigma 8. Combining weak lensing S8 with redshift space distortion F sigma 8 measurements from the same surveys provides a more complete picture of how structure is growing, and the combined constraints consistently point towards somewhat less growth than Planck predicts. The 2 tensions together, Hubble at 5 sigma, S8 at 2 to 3 sigma across 3 independent surveys, represent simultaneous failures of the standard model in 2 different observational sectors. Solutions to one tend to worsen the other, suggesting the model's degrees of freedom are not independent and that a single new piece of physics needs to simultaneously explain both. Galaxies are not simply carried along by cosmic expansion, like raisins in rising bread. They have additional velocities, peculiar velocities, driven by the gravitational pull of nearby concentrations of matter and the repulsion of nearby underdense voids. A galaxy cluster falls toward a nearby supercluster of galaxies. Galaxies at the edge of a void stream outward, away from it. The statistical properties of these additional motions, how large they are, how far they remain coherent, which direction they point, are specific predictions of the standard model. The key prediction for large scales is that coherent bulk motions should diminish rapidly above a scale of about 300 to 400 million light-years. At larger scales, the universe should be sufficiently smooth that there is no net preferred direction for streaming. Any large enough volume of galaxies should have peculiar velocities that average out to roughly zero, because the gravitational landscape is the same in all directions at those scales. In 2008, a research team published evidence for a bulk flow extending across several billion light-years in a consistent direction, far beyond the scale, where lambda CDM expects coherent streaming. They used the kinetic Sunyaev-Zeldovich effect, a subtle distortion that moving galaxy clusters imprint on microwave background photons passing through their hot gas, as their tracer. By stacking this signal across hundreds of clusters and looking for a consistent directional pattern, they inferred an organized motion they called dark flow, implying some enormous gravitational influence, perhaps beyond the observable horizon, pulling matter in one direction. The subsequent literature has been genuinely split. Some analyses of independent peculiar velocity datasets find excess bulk flows. Others find flows consistent with the standard model once systematic errors in distance measurements are carefully treated. The Cosmic Flows 4 compilation, released in 2023 and representing the largest and most carefully assembled peculiar velocity catalog in existence, has been analyzed by multiple groups with differing conclusions. Some find bulk flows exceeding lambda CDM predictions on scales of several 100 million light-years. Others find consistency with the model within uncertainties. The implications of genuine excess bulk flows extend to the question of what the universe looks like beyond our observable horizon. If coherent motions persist to scales approaching 1 billion light-years, and if the standard model correctly describes the matter distribution within the observable universe, then there must be mass concentrations outside our horizon that are gravitationally influencing what we can see. The observable universe is not a closed system. Gravitational forces do not respect the boundary imposed by the speed of light traveling for 14 billion years. Structures that formed beyond our horizon during the inflationary epoch can still exert gravitational forces on matter within our horizon, potentially driving coherent motions that have no identifiable source within the observable volume. The tension is not resolved. If genuine excess bulk flows exist on scales approaching 1 billion light-years, they could indicate gravitational attraction from structures beyond our measurement range, real large-scale departures from homogeneity, or systematic effects in how distances are measured. Future surveys with the Vera Rubin Observatory and other large-scale structure missions will provide the data quality to test these possibilities definitively. In the first few minutes after the Big Bang, the universe was a nuclear furnace operating at temperatures and densities that cannot be replicated in any laboratory on Earth. The conditions were sufficient to fuse free protons and neutrons into the simplest atomic nuclei, hydrogen, a single proton, formed in the largest quantities and still makes up the vast majority of ordinary matter in the universe. Helium nuclei formed as well, and the standard model predicts that they should account for about 24% of the ordinary matter mass by the time nucleosynthesis ended 20 minutes after the Big Bang. Measurements of helium abundances in old, pristine astronomical environments confirm this prediction with beautiful accuracy. Deuterium, a heavy form of hydrogen with 1 proton and 1 neutron, was also synthesized in predicted quantities that match observations in ancient gas clouds to within observational errors. Lithium, 7, is the exception. Big Bang nucleosynthesis calculates a specific primordial abundance for lithium, 7, based on the baryon density of the universe, a quantity precisely determined from the Planck satellite's microwave background measurements. The prediction is about 4 times 10 to the negative 10 lithium, 7 atoms relative to hydrogen. When astronomers measure lithium 7 inches, the oldest known stars, population 2 stars, formed from material barely processed by earlier stellar generations, preserving close to the original primordial composition, they consistently find an abundance roughly 3 times below this prediction. These old stars define what is called the Spite Plateau over a wide range of stellar temperatures and metallicities. The observed lithium 7 abundance sits at a consistent value that is substantially below the nucleosynthesis prediction. The plateau itself is evidence that the lithium in these stars reflects a primordial abundance rather than an altered one. The consistency across different stars argues against large systematic depletion. Yet the plateau value and the predicted value disagree by a factor of 3. This discrepancy has persisted for more than 20 years. 3 categories of explanation have been pursued. First, lithium could be slowly destroyed inside stars through mixing processes that carry material from the surface down to hotter interior layers where lithium burns. The spite plateau constrains how uniform this process must be across very different stellar types, which places tight limits on how efficiently it operates. Second, laboratory measurements of the nuclear reaction cross-sections used in nucleosynthesis calculations could be incorrect at the relevant energies, though dedicated experiments have refined these without resolving the discrepancy. Third, new physics, operating in the first 20 minutes of the universe, exotic particle decays, modified nuclear physics, non-standard thermal histories, could have altered lithium production or destruction in ways not captured by the standard nucleosynthesis framework. The lithium problem has an observational nuance that makes it more robust than it might appear at first. The spite plateau, the constant lithium abundance observed across a wide range of old stars of different temperatures and compositions, is itself evidence that the lithium in these stars has not been significantly depleted from its original value. If stellar mixing were destroying lithium inside these stars, the amount of depletion would be expected to correlate with stellar properties like temperature and rotation rate, producing a range of lithium abundances rather than a plateau. The remarkable flatness of the plateau argues that the observed value is the primordial one, not a depleted remnant. If the plateau truly represents the primordial abundance, then the nucleosynthesis prediction is genuinely wrong by a factor of 3, and the explanation must lie in the physics of the first 20 minutes of the universe. The lithium problem is not the most dramatic anomaly in this story, but its persistence over 20 years and its location in one of the most theoretically clean and constrained sectors of cosmology gives it disproportionate weight. It is a problem that should have been solved by now. At the deepest level, the universe's existence as a place filled with matter, rather than empty radiation, is itself an anomaly that the standard model cannot explain. The Big Bang produced energy and particles. The fundamental symmetry between matter and antimatter in the standard model of particle physics implies that it should have produced them in equal quantities, one particle for every antiparticle. When matter and antimatter meet, they annihilate into pure photons, converting all their mass into radiation. If the Big Bang had been perfectly symmetric, every proton would have found its antiproton partner, every electron its anti-electron, and the universe would have annihilated itself completely into a bath of photons with no matter remaining. No atoms, no chemistry, no stars, no planets, nothing. The universe is not empty. The universe is full of matter. For every billion antiparticles in the early universe, there was apparently one extra matter particle, a fractional asymmetry of 1 part in a billion that survived all the annihilations. That one extra particle in a billion, multiplied across the entire observable universe, produced every atom of matter that has ever existed, every star, every planet, every molecule of every living thing. Where did that 1 in a billion asymmetry come from? The standard model does contain a small violation of the symmetry between matter and antimatter, called CP violation, measured precisely in specific weak force interactions involving certain mesons. This CP violation is real and experimentally confirmed, but it is insufficient by many orders of magnitude to generate the observed matter-antimatter imbalance. The standard model's CP violation is negligible as an explanation for the existence of matter. Something beyond the standard model, new physics, that operated in the first fractions of a second after the Big Bang must have generated the asymmetry. Proposed mechanisms include leptogenesis, in which a heavy neutrino asymmetry was created at high energies and later converted into the matter asymmetry through known particle physics processes. Electroweak baryogenesis, which would require the electroweak phase transition to have been violent and first order rather than the smooth crossover. The Standard Model predicts for the measured Higgs mass and more exotic scenarios involving entirely new particle sectors interacting with the known one. The search for baryogenesis mechanisms is intimately connected to searches for new particles at accelerators, but the connection is subtle. Most baryogenesis scenarios require heavy particles that decayed in the first fractions of a second of the universe. At the temperatures of that era, the relevant particles would have been produced thermally, but they are too heavy to be produced at current accelerators. The best hope for experimental progress is not to produce these particles directly, but to observe low-energy consequences of their existence, such as CP violation in decays of known particles, or small corrections to Standard Model parameters that would signal the presence of physics above the energy scale currently accessible. The search for these indirect signatures is a major motivation for precision measurement programs at multiple facilities worldwide. None of these mechanisms has been confirmed experimentally. No new particle predicted by the specific mechanisms has been detected at the LHC or other accelerators. No rare decay or violation has been measured that requires these extensions. The matter-antimatter asymmetry remains one of the most profound open questions in physics, and the universe's continued existence as a matter-filled place is, in a deep technical sense, evidence for physics beyond the Standard Model that we have not yet found. Between the glowing filaments of the cosmic web lie vast regions of emptiness. These cosmic voids are not merely sparse, they are genuinely underdense stretches of space, spanning hundreds of millions or even billions of light years, containing far fewer galaxies than average regions of the universe. Inside these voids, the processes that generate magnetic fields in normal cosmic environments are essentially absent. No stars explode as supernovae to send magnetic shockwaves through surrounding gas. No galaxy disks churn and amplify fields through their stellar dynamos. No jets from active galactic nuclei thread magnetic structure through the medium. By every physical expectation, the diffuse intergalactic gas inside cosmic voids should be magnetically quiet to the point of irrelevance. Observations tell a different story. The evidence comes from gamma-ray astronomy in a roundabout way. Very distant blazars, active galactic nuclei whose jets point almost directly toward us, emit high-energy gamma rays that travel across billions of light years. On that process, the gamma rays occasionally collide with lower-energy infrared photons from other galaxies, creating electron-positron pairs in a process called pair production. These newly created electrons and positrons carry the original gamma-ray energy and quickly radiate it away as secondary gamma rays at lower energies, arriving at our detectors slightly spread in angle around the original source position. If no magnetic field exists in the intergalactic space those electrons and positrons traveled through, they radiate their energy almost straight forward, producing a halo of secondary emission tightly concentrated around the blazar. If a magnetic field is present, even a very weak one, it deflects the charged electrons and positrons as they travel, spreading the secondary emission into a larger, more diffuse halo. When astronomers analyzed the patterns of secondary emission from multiple distant blazars, they found that the halos were more spread than zero magnetic field predicts. The data require a coherent intergalactic magnetic field in cosmic voids at a strength of at least 10 to the negative 15 Tesla, extraordinarily weak by any everyday standard, but coherent across scales of millions of light years. In regions of space where no known astrophysical process can generate magnetic fields, coherent fields exist. Observations of this kind of void magnetic field also help constrain models of magnetogenesis, the theoretical processes by which magnetic fields were generated in the early universe. If the fields are truly primordial, they carry information about the energy scale and duration of the process that created them. A field generated during inflation would have a specific correlation length and amplitude relationship that differs from one generated during the electroweak phase transition, which differs again from one generated during the quark-hadron transition. The specific properties of the void fields, inferred from blazar gamma-ray halos, their coherence length, their amplitude, and how their strength varies between different voids, could in principle distinguish between these scenarios. This makes void magnetic field observations a potential probe of physics from the first fractions of a second of cosmic history. The only plausible origin for fields, this ancient and this widespread in the deepest voids, is the early universe itself. A primordial magnetic field generated during inflation or during the electroweak or quark-hadron phase transitions in the first fractions of a second after the Big Bang could have seeded the cosmos with a faint but coherent field that survived dilution by expansion to persist in voids today. If this interpretation is correct, these void magnetic fields are direct observational relics of physics operating in the first microseconds of the universe's existence, processes entirely outside the standard cosmological model. A new chapter in early universe physics would need to be written to explain them. The James Webb Space Telescope launched in late 2021 and returned its first scientific images in mid-2022. Astronomers had carefully calibrated expectations. Webb would see deeper and sharper than any previous instrument, revealing the faint, young galaxies of the very early universe in detail that previous missions could only glimpse. The standard model predicted these early galaxies would be small, diffuse, irregular, the barely assembled infants of a universe just beginning to form structure through the slow hierarchical accumulation of matter. A few 100 million years after the Big Bang, galaxies should still be works in progress, not finished products. Webb's first deep field images contradicted that expectation immediately. The early data revealed galaxies at extremely high redshifts, corresponding to epochs just a few 100 million years after the Big Bang, that appeared surprisingly bright, surprisingly compact, and surprisingly massive. In early analyses, some objects appeared to contain stellar masses comparable to the Milky Way, concentrated into regions far smaller than expected, given how recently, on cosmic timescales, they would have needed to form. The number of these unexpectedly massive early objects exceeded theoretical predictions by factors of 10 or more in some analyses. Subsequent work has refined the initial excitement with careful scrutiny. Some early candidates turned out to be at lower redshifts than initially estimated, and some apparent stellar masses were revised downward. But even after extensive reanalysis, a statistically significant excess of bright, massive early galaxies remains across multiple independent teams using multiple analysis frameworks. The standard model of hierarchical structure formation, in which galaxies grow slowly from small building blocks merging over billions of years, has difficulty producing such massive galaxies so early. Several explanations are being explored. The star formation efficiency in the early universe may be dramatically higher than standard feedback models predict, allowing early galaxies to convert gas into stars much faster. Primordial density fluctuations may be larger at specific scales than simple inflationary models predict, providing deeper gravitational wells that accelerate early assembly. Massive seed black holes formed in the first cosmic moments could have driven rapid star formation through their energetic feedback. Each explanation requires physics that is not in the standard model as currently formulated. The Webb observations of early massive galaxies have also revealed surprisingly massive black holes in the centers of some of these systems. Active galactic nuclei, shining at luminosities that imply black hole masses of hundreds of millions to billions of solar masses at epochs less than a billion years after the Big Bang. Standard astrophysical models of black hole growth through accretion struggle to produce black holes this massive so quickly. a black hole accreting at the theoretical maximum rate, starting from a stellar mass seed of about 10 solar masses, takes approximately 1 billion years to grow to a billion solar masses. Finding billion solar mass black holes at ages of 700 million years implies either above maximum accretion rates or much heavier initial seeds, or both. The Webb discoveries have made the problem of early black hole formation significantly more acute. The Webb anomaly is young. The field is still working through its implications, but the pattern is consistent with multiple other signals that have been building for years. Something about the universe's early structure formation is not matching our model. If galaxies form too fast and too massive in the early universe, it would be unsurprising to also find large-scale structures that exceed what the model says the universe can build. And that is precisely what surveys have been finding with increasing regularity and increasing statistical weight. The cosmological principle, combined with the standard model's description of structure growth, predicts that the universe should become statistically homogeneous, smooth and featureless, above a scale of about 300 to 400 million light-years. Below that scale, galaxies and clusters and superclusters can form distinct, non-random patterns. Above it, the universe should average out. Any sufficiently large volume should look statistically similar to any other, because the largest density fluctuations from inflation are too small at that scale to produce coherent structure. In 2021, Alexia Lopez reported the giant arc, a curved structure of galaxies, galaxy clusters, and gas spanning roughly 3 billion light-years in length, located about 9.5 billion light-years away. Lopez found it by analyzing galaxy spectra from the Sloan Digital Sky Survey and noticing a conspicuous concentration of objects at the same distance, spanning an enormous angular extent on the sky. The structure's length is roughly 10 times the theoretical maximum scale for coherent cosmic structures under lambda CDM. Statistical analysis of its probability under standard models gives a value around 1 in 50,000. That is not a subtle deviation at the edge of significance. 1 in 50,000 is a screaming signal. The Hercules Corona Borealis Great Wall, first reported in 2013 and expanded in subsequent analyses, is more extreme still. A proposed structure spanning roughly 10 billion light-years if confirmed, representing a substantial fraction of the entire observable universe's diameter. Establishing its true extent and coherence has been difficult because of its enormous angular size, and whether it is a single connected structure or a chance alignment of multiple separate overdensities is still debated. The giant arc discovery by Alexia Lopez is both a statistical challenge to the standard model and visually striking in the survey data. A curved band of galaxy concentrations spanning an enormous angle on the sky, clearly visible once the eye knows where to look. Lopez spotted it during routine analysis of galaxy spectra and noted its improbability before publishing. The structure's discovery highlighted how serendipity still plays a role in modern data-driven astronomy. The giant arc was present in existing survey data for years before anyone recognized its nature and extent. With automated search tools now looking systematically for such structures in upcoming surveys, the catalogue of potential large-scale anomalies is likely to grow, providing stronger statistical constraints on whether giant structures are rare fluctuations or signs of something systematically wrong with our homogeneity assumptions. Other enormous structures, the Sloan Great Wall, the Boss Great Wall, the South Pole Wall, have each in their time challenged the expected homogeneity scale. The pattern across surveys is consistent. Every time a deeper or wider galaxy survey is completed, new enormous structures emerge at scales that approach or exceed the theoretical maximum. Either the universe homogenizes at a far larger scale than lambda CDM predicts, or the transition to homogeneity does not exist at the scales we have been examining. If the latter, the cosmological principle fails at its most basic observational test. The coincidence problem does not involve a mismatched measurement or an anomalous structure. It involves time, specifically, the particular moment in cosmic history at which we find ourselves. And the more carefully you examine it, the more uncomfortable it becomes. The universe contains two dominant energy components: matter and dark energy. Matter, dark and ordinary combined, behaves straightforwardly under expansion. As the universe grows larger, the same amount of matter is spread through a larger volume, and its energy density decreases. Dark energy, under the cosmological constant interpretation, does not dilute this way. It remains constant per unit volume even as the universe expands, because it is a property of space itself rather than of the matter within it. These two very different behaviors mean their ratio changes dramatically over cosmic history. In the early universe, matter dominated overwhelmingly. Dark energy existed but was negligible against the dense matter of the young cosmos. As expansion continued and matter diluted, dark energy's fractional contribution grew. Today, dark energy accounts for about 68% of the total energy budget, while matter represents about 27%. The two components crossed rough parity within the last few billion years. In the future, as expansion continues and matter dilutes further, dark energy will become increasingly dominant until matter is a negligible trace in a universe governed almost entirely by the energy of empty space. We live in the brief transitional window. Right now, not a billion years ago, not a billion years from now, but precisely at the cosmic epoch containing the first complex observers. Matter and dark energy are in rough balance. The coincidence problem asks why. There is no obvious physical reason why observers should find themselves at this specific moment rather than at any other. The most common attempted resolution is anthropic: complex structure, stars, planets, chemistry. Observers can only form during a matter-dominated era, where gravity can assemble and hold together the necessary structures. Once dark energy completely dominates and expansion accelerates without limit, no new stars can form and no new complexity can arise. So observers will naturally find themselves in the matter-dominated or recently transitioned era, because those are the only epochs compatible with their existence. The coincidence problem becomes more acute when you consider the precise timing involved. The transition from matter domination to dark energy domination, the moment when they crossed rough parity, occurred approximately 5 billion years ago. Complex life on Earth emerged roughly 4 billion years ago. The two timescales are separated by only about a billion years, which is tiny compared to the 14 billion year age of the universe and the trillion year timescales over which dark energy will continue to operate into the future. An observer who appeared 1 billion years earlier would have found a matter-dominated universe. An observer appearing 10 billion years from now would find a dark energy-dominated universe in which galaxy formation has long since ended. We appear in the narrow window where complex structure exists and dark energy is just beginning to dominate. Whether this is selection, coincidence, or hidden physics remains undecided. The anthropic argument requires a multiverse or many cosmic epochs to draw selection from, and it leaves a philosophical unease. The universe's most prominent feature at the moment of observation may not have a physical explanation accessible to science. The coincidence problem is the most honest reminder in cosmology that some questions may permanently reside at the boundary between physics and philosophy. The laws of physics are assumed to be universal. The fine structure constant, which governs the strength of electromagnetic interactions and determines the structure of atoms, the binding energies of electrons, and the wavelengths of spectral lines, has a specific value of approximately 1 divided by 137. Every atom everywhere in the universe should operate according to this same number. Chemistry, light, matter itself would be entirely different things if this number were significantly different. To test whether the constant has actually been fixed across cosmic time and space, astronomers use one of nature's most convenient laboratories, the spectra of light from distant quasars. As this light travels billions of light years toward us, it passes through intervening clouds of gas, and the atoms in those clouds absorb light at specific wavelengths determined by their electronic transition energies. Those transition energies depend on the fine structure constant at the time and place of absorption. By comparing the observed absorption wavelengths to laboratory measured values, physicists can probe whether the constant has drifted over cosmic time or varies across different directions on the sky. Several research teams have reported hints of spatial variation, slightly different apparent values of the fine structure constant when looking in different directions on the sky, at the level of a few parts per million. Provocatively, the direction of the claimed variation is roughly consistent with the axis of evil direction identified in the microwave background and with the cosmic dipole anomaly. 3 independent anomalies pointing in approximately the same direction would be difficult to explain as coincidence. The experimental search for variation in fundamental constants has expanded well beyond quasar spectroscopy to include a variety of complementary approaches. Laboratory comparisons of atomic clocks of different types, which have different sensitivities to the fine structure constant, can detect tiny drifts in its value over years of observation. The Oklo Natural Nuclear Reactor in Gabon, which operated about 2 billion years ago, left isotopic ratios in surrounding rocks that can be compared to predictions assuming the nuclear physics of 2 billion years ago matched today's. Analysis of the Oklo data places very tight constraints on how much certain nuclear binding energies, which depend on the fine structure constant and the strong coupling constant, could have changed over the last 2 billion years. These multiple lines of evidence together build a more comprehensive picture of which types of fundamental constant variation are still possible. Independent checks using different quasar datasets and different analysis methods have not consistently confirmed the fine structure variation. The current scientific consensus is that any variation is at or below the measurement uncertainty, and no confirmed detection has been established. But the consistency of the claimed direction across independent searches keeps the question alive. A confirmed spatial variation in fundamental constants would mean the laws of physics themselves are not uniform across the observable universe. That distant regions of the cosmos operate by rules that differ slightly from what we measure here. The foundation of science, the assumption that physics is universal, would need revision. The cosmological principle is the load-bearing wall of all of modern cosmology. It states that the universe is homogeneous and isotropic at sufficiently large scales, the same density in every direction, the same density at every location. Without this principle, the equations of general relativity describing cosmic expansion cannot be applied globally. The calculations of distance from redshift, the interpretation of the Hubble constant, the use of the microwave background as a record of early conditions. Every major tool in the cosmologist's kit assumes this principle holds. The principle has not been rigorously demonstrated. It was assumed because early observations were consistent with it, and because it enormously simplified the mathematics. As observations improved, inconsistencies began to accumulate from multiple independent directions. The cosmic dipole anomaly in radio sources and quasars finds a preferred direction at 5 sigma significance. The axis of evil in the microwave background finds a consistent preferred direction at less than 1% probability under isotropy. Giant structures like the Giant Arc and the Hercules Corona Borealis Great Wall suggest the universe does not homogenize at the scales lambda CDM predicts. The CMB cold spot marks a specific region of the sky as anomalously cold with less than 1% chance probability. Hints of spatial variation in the fine structure constant suggest possible regional differences in physics. Bulk flow anomalies suggest coherent motion across scales beyond the predicted coherence length. No single anomaly definitively breaks the cosmological principle. Each one carries its own systematic uncertainties and its own skeptics. But they are not independent. They have been accumulating simultaneously across independent instruments, independent surveys, and independent physical processes over a span of 2 decades. The pattern is consistent enough that it can no longer be individually dismissed without addressing why all these independent probes are consistently finding trouble in the same conceptual direction. The failure of the cosmological principle, if confirmed by future surveys, would not leave cosmologists without tools. Cosmological frameworks that do not assume isotropy and homogeneity exist. They are simply much more complex to work with. The Lemaitre-Tolman-Bondi models, for instance, describe a spherically symmetric but radially inhomogeneous universe. Bianchi models describe universes with specific types of anisotropy. These models have been studied as theoretical alternatives, and some have been used to test whether specific features of the microwave background are compatible with inhomogeneous or anisotropic universes. The challenge is that dropping the cosmological principle enormously expands the space of possible models and makes the extraction of clean physical inferences from observations much harder. The principle was adopted partly for its simplicity, and replacing it requires accepting a much more complicated universe. If the cosmological principle fails at observable scales, cosmology needs a new foundation, one that can accommodate large-scale anisotropy while still explaining everything the standard model gets right. That is a major reconstruction, and no one has yet proposed a framework that achieves it convincingly. When physicists propose solutions to the Hubble tension, they typically introduce some form of new physics in the early universe that modifies the expansion rate before the microwave background was imprinted. The most extensively studied such proposal is early dark energy. A brief component of dark energy that existed in the early universe contributed significantly to the expansion rate around the time of recombination, then diluted away and became negligible. If early dark energy boosted the expansion rate at that epoch, the sound horizon, the scale that Planck uses to infer the Hubble constant, would be smaller than the standard model assumes, and the inferred expansion rate would shift upward toward the distance ladder value. The mechanism is physically motivated. Models can be constructed where the early dark energy is a scalar field that rolls down a potential, briefly mimicking dark energy before becoming negligible. The mathematics is tractable, and in some regions of parameter space, the Hubble tension is meaningfully reduced. The problem is what early dark energy does to everything else. Injecting extra energy into the early universe does not only shift the sound horizon, it also changes the way structure grows afterward. In particular, it tends to increase the amplitude of density fluctuations, pushing S8 upward at exactly the moment when the observations of weak gravitational lensing are finding S8 to be too low. Solving the Hubble tension with early dark energy worsens the S8 tension. The two anomalies are connected. Pull the model in one direction to fix one crack, and the other crack opens wider. This interconnection is one of the most telling features of the current cosmological crisis. The standard model's parameters are not independent dials that can each be adjusted freely. They are linked through the underlying physics of expansion, structure, growth, and radiation pressure. A model that successfully resolves one tension while maintaining all other constraints has been exceptionally difficult to construct. The history of proposed solutions to the Hubble tension provides a useful map of the conceptual territory. Early dark energy, decaying dark matter, modified gravity, extra-relativistic species, neutrino self-interactions, mirror dark matter, and dark sector phase transitions have all been proposed and analyzed. Each model has been tested against the full suite of cosmological observations across all cosmological probes, including the Hubble constant measurements. Each has found regions of parameter space where the tension is reduced, and each has found constraints from other observations that limit how much parameter freedom is actually available. The inability of any single model to thread all the needles cleanly has led some researchers to propose that the solution involves a combination of effects, perhaps a small amount of early dark energy, combined with a modification to the late universe equation of state, each contributing a partial fix. Multi-component solutions are harder to motivate theoretically, but may be what the data is actually demanding. Some classes of models involving interacting dark energy, modified neutrino physics, or changes to the recombination process itself can reduce both tensions simultaneously in limited regions of parameter space. None has been established as the correct solution. Each requires a specific mechanism that introduces new parameters without clear theoretical motivation. The field is hunting for a single, elegant addition to the standard model that threads all the needles at once. So far, the needle keeps slipping. If cold, dark matter has specific problems at small scales, the natural question is whether a different kind of dark matter, one with modified properties, could fix those problems while preserving the large-scale successes. Several candidates have been studied intensively, each with distinct properties and testable predictions. Warm dark matter replaces the slow-moving particles of standard lambda CDM with particles possessing higher thermal velocities. These faster particles cannot be confined to structures below a certain scale. Their thermal motion disrupts small halos before they can form. The result is a natural suppression of small-scale structure, fewer satellite galaxies, smoother central profiles. Warm dark matter successfully reduces the small-scale discrepancies in galaxy counts without disturbing the large-scale structure that cold, dark matter fits well. The constraint on how warm the dark matter can be comes from the Lyman alpha forest, the absorption pattern that intergalactic hydrogen leaves in quasar spectra, which encodes information about the small-scale matter distribution, and current constraints allow warm, dark matter in a narrow mass window. Self-interacting dark matter gives dark matter particles a force between themselves, not gravity, but a new force specific to the dark sector. Standard cold dark matter particles pass through each other without any interaction, like a gas of particles with zero collision cross-section. Self-interacting particles scatter off each other, causing the dark matter to thermalize inside halos, puffing up central densities and converting cuspy profiles into cores. With the right interaction strength, the core cusp problem and the too big to fail problem can both be reduced. The challenge is that the required cross-section is large enough to have observable effects in galaxy clusters as well, and cluster observations place tight constraints on self-interaction strength. Fuzzy dark matter is the most radical alternative. It proposes that dark matter consists of ultralight bosons, particles with masses so tiny that their quantum mechanical wavelength is comparable to the size of a dwarf galaxy. At this mass scale, dark matter behaves less like a collection of discrete particles and more like a continuous quantum wave field, with quantum pressure opposing further compression below a characteristic scale. Small halos cannot form because the quantum pressure prevents collapse. Central cusps cannot develop because quantum uncertainty smears out the density profile. The model is elegant, but the mass range where it solves small-scale problems is constrained by Lyman alpha forest observations that probe the small-scale matter distribution at high redshift. The different dark matter models generate distinct, testable, observable predictions for specific astronomical systems that ongoing surveys are actively testing. Self-interacting dark matter, for instance, predicts that galaxy clusters undergoing mergers, like the Bullet cluster, but observed over a longer baseline of merger history, should show dark matter halos that have experienced scattering events and have more rounded, spherical shapes than the elongated halos produced by collisionless dark matter. Weak lensing shape measurements of cluster halos in large cluster samples are precisely the kind of data that can discriminate between self-interacting and collisionless dark matter. Fuzzy dark matter predicts specific granular substructure in dark matter halos that would produce observable fluctuations in the surface brightness of gravitationally lensed arcs. The predictions are concrete and the tests are underway. All three alternatives generate distinct, testable predictions. The Vera Rubin Observatory and the Euclid satellite will provide the precision measurements of small-scale structure and satellite population statistics needed to test them. In the first microseconds after the Big Bang, the universe was so hot and dense that even the concept of ordinary matter did not apply. The conditions were extreme enough that direct gravitational collapse could form black holes from density fluctuations in the primordial plasma, not the collapse of dying stars, but the spontaneous implosion of overdense regions in the radiation-dominated early cosmos. These are primordial black holes, and their possible existence has moved from theoretical curiosity to active observational target. The detection of gravitational waves from black hole mergers by LIGO and Virgo, beginning in 2015, gave primordial black holes renewed attention. Several of the detected mergers involved black holes with masses in ranges that are difficult to explain through standard stellar evolution, masses in the tens of solar masses and above, in the so-called upper mass gap, where standard stellar collapse is not expected to produce black holes efficiently. Primordial black holes formed in the early universe would naturally span a broad mass distribution that could populate these unusual mass ranges. Extensive observational searches have constrained primordial black holes significantly. Gravitational microlensing surveys, which monitor millions of stars in the Milky Way and its satellite galaxies for transient brightening events caused by compact objects passing in front of them, have ruled out primordial black holes as the dominant dark matter component across most mass ranges. The gamma-ray background, gravitational wave event statistics, and cosmic microwave background constraints from the era of primordial black hole formation add further limits. Small windows remain open, particularly in the mass range around 1/100th of a solar mass to a few solar masses. Primordial black holes sit in an unusual position in the landscape of cosmological anomalies because they are simultaneously a solution to several puzzles and a source of new constraints. As a partial dark matter component, they could address the early massive galaxy problem by providing seed masses. As a possible contributor to the gravitational wave background, they generate testable signatures in future LISA observations. As objects formed in the very early universe, they encode information about the primordial power spectrum on scales much smaller than those probed by the microwave background or galaxy surveys. If primordial black holes constitute even a small fraction of the dark matter, the implications ripple through multiple fields simultaneously. The fact that their existence has not been confirmed or ruled out in the most interesting mass ranges makes them one of the more tantalizing open possibilities in early universe cosmology. Even if primordial black holes make up only a fraction of the dark matter, they could serve a crucial function as seeds for the supermassive black holes that appear at the centers of massive galaxies, including the early massive galaxies Webb has been finding at high redshift. Standard astrophysical mechanisms for growing supermassive black holes, from stellar remnants through accretion, face serious timing constraints. There is simply not enough time between the Big Bang and the epochs when Webb sees massive black holes in place to grow them from small initial seeds. A head start from primordial black holes formed seconds after the Big Bang changes that calculation fundamentally, and future gravitational wave observatories will provide much stronger constraints on whether such a population exists. The 2024 DESI dark energy results arrived during one of the most active periods of cosmological data collection in history. Multiple major surveys were simultaneously producing results across different probes of cosmic structure, and the DESI signal for dynamical dark energy did not arrive in isolation. It arrived alongside converging hints from weak gravitational lensing, baryon acoustic oscillations in independent datasets, and theoretical frameworks that had been predicting exactly this kind of evolution for years. The signal itself is not a discovery by particle physics standards. 2.5 sigma means roughly a 1 in 80 chance of a statistical fluctuation, but the direction has appeared in multiple analyses, and the theoretical implications of confirmation are so significant that the community is treating it as a priority investigation for every instrument coming online in the next decade. A dynamical dark energy field has a different Haas future than a cosmological constant. Under the constant interpretation, the universe expands forever, growing emptier and colder through an unimaginable span of time until the last black holes evaporate in a final whisper of Hawking radiation and the universe reaches maximum entropy. This is the heat death scenario: quiet, cold, and irreversible. Under a dynamical field, the future is less certain. The field could strengthen, pushing expansion faster until even atoms are torn apart in a Big Rip event. It could weaken and reverse, allowing gravity to eventually overcome expansion in specific regions or throughout the entire cosmos. It could oscillate, cycling between phases of acceleration and deceleration. The shape of the dark energy equation of state over the next few billion years determines which of these futures actually unfolds. The cosmological implications of DESI's dark energy results extend to the question of whether dark energy and dark matter might be connected in a way the standard model does not capture. In the standard model, dark energy and dark matter are completely independent components. Dark energy is a property of empty space. Dark matter is a particle component of matter, but some theoretical frameworks allow them to interact. Dark energy can decay into dark matter, or they can exchange energy through a coupling. Such interactions would modify both the expansion history and the growth of structure in correlated ways, potentially explaining why both the Hubble tension and the S8 tension appear simultaneously. If DESI's dark energy signal is confirmed and found to follow a specific evolution with time, it could discriminate between a pure quintessence field and a model with dark sector interactions. The DESI mission will continue collecting data. Euclid is mapping the universe's large-scale structure from space. CMB experiments with increasing sensitivity will constrain the physics of the early universe more tightly. Together, these instruments will either confirm or rule out dynamical dark energy within this decade. If confirmed, cosmology will need a theory, a real physical mechanism that explains what the dark energy field is, what symmetry governs its behavior, and why it has the specific properties we measure. That theory does not currently exist. Bring all the anomalies together: the Hubble tension at 5 sigma, the S8 tension at 2 to 3 sigma across 3 independent surveys, the axis of evil in the microwave background, persistent through 2 satellite missions and 2 decades of analysis, the CMB cold spot at below 1% probability, the cosmic dipole excess at 5 sigma in over 1 million quasars, early massive galaxies in Webb's deep fields, giant structures like the 3 billion light-year giant arc, possible cosmic bulk flows exceeding predictions, the cosmic lithium problem, over 20 years old, primordial magnetic fields in cosmic voids, hints of dynamical dark energy from DESI, the matter-antimatter asymmetry, unresolved for 60 years, possible spatial variation in the fine structure constant. Each anomaly, arrived from a different instrument, was measured by a different team and probes a different aspect of the universe. None was designed to tell a story with the others. Yet, they are all telling the same story. The standard model is incomplete in ways that are now statistically undeniable. The combined picture is not of a model with one flaw, easily patched. It is a model with a cluster of independent failures across multiple scales and epochs that resist any single proposed solution. Attempts to fix the Hubble tension worsen the S8 tension. Attempts to explain the axis of evil as foreground contamination leave the cosmic dipole anomaly unexplained. Modifications to dark matter that help with small-scale galaxy structure have no obvious connection to why JWST sees massive early galaxies. The anomalies feel like pieces of a puzzle, but the picture on the box has not yet emerged. The convergence of anomalies explored throughout this story, from the Hubble tension to the axis of evil to the JWST early galaxies to the giant arc, all point in the same general direction, and that direction has a name in the cosmological literature: beyond lambda CDM. This phrase does not mean the current model is wrong in all its predictions. It means the model is incomplete in specific ways that are now becoming measurable. The question of what goes beyond lambda CDM is the central theoretical challenge of the current era. The answer might be one new component, a dynamical dark energy field with a specific equation of state, or several, dark matter with self-interaction, plus modified gravity on large scales, plus a refinement of inflationary predictions. The instruments being built and deployed right now will provide the data. The theorists are already working on the frameworks. The resolution, whatever form it takes, is coming. That convergence of independent signals is what makes the current moment in cosmology unusual. The history of science contains many single anomalies that eventually vanished with better data. A dozen simultaneous independent anomalies pointing in the same general direction toward a model that is systematically incomplete is something different, something more. Lambda CDM was built on a small number of foundational assumptions. That general relativity correctly describes gravity at all scales. That dark matter is cold and collisionless. That dark energy is a cosmological constant, and that the universe is isotropic and homogeneous at large scales. These assumptions were not arbitrary. They were the simplest choices consistent with available data at the time, and they led to a model of remarkable predictive power, fitting observations that span from the first minutes of existence to the present day across a dynamic range of size and energy that no other physical theory approaches. Lambda CDM earns its status as science's most complete cosmological description. What the anomalies are revealing, one by one, is that some of these foundational assumptions may be approximations rather than exact truths. Dark energy may be a dynamical field rather than a constant. Dark matter may have properties beyond simple gravitational interaction. The universe may have large-scale structure above the homogeneity scale. General relativity may behave differently on cosmic scales than it does locally. Any one of these modifications, if confirmed, would require a systematic revision of the standard model. Multiple confirmed modifications would require something closer to a new framework. The researchers confronting these anomalies are not looking for trouble. They are physicists and astronomers who spent careers helping build Lambda CDM, who understand its successes better than its critics, and who are being forced by their own instruments to confront its failures. They approach each anomaly with appropriate skepticism. They audit their methods, hunt for systematic errors, and demand replication before drawing strong conclusions. The fact that the anomalies have survived this process, that 5 sigma signals remain at 5 sigma after years of scrutiny, is precisely what makes them compelling. The next generation of instruments is already in motion. The Vera Rubin Observatory will survey billions of galaxies, testing the small-scale predictions of dark matter models and the large-scale predictions of homogeneity and structure growth. Euclid is mapping hundreds of millions of galaxy shapes to constrain dark energy and measure the S8 parameter with new precision. CMB S4 will produce microwave background maps orders of magnitude more sensitive than Planck's. The square-kilometer array will survey radio sources across the entire sky, giving the cosmic dipole measurement the statistics needed to either confirm the anomaly at unambiguous significance or close it definitively. The final lesson from the accumulation of anomalies is about the nature of scientific confidence. Lambda CDM is simultaneously the most successful and the most thoroughly scrutinized cosmological framework in history, and the scrutiny has revealed real problems. This is not a reason for skepticism about science. It is science working exactly as designed. The history of physics is the history of successful models that revealed their limits under sharper testing, giving way to more comprehensive frameworks that explained both the old successes and the new failures. Newtonian gravity was not wrong for 2 centuries. It was approximately right, and general relativity revealed both why it worked so well and where it failed. Lambda CDM is not wrong about the cosmic web or the microwave background or the light element abundances. It is approximately right, and whatever comes next will need to explain both its extraordinary successes and the specific ways it falls short. The universe does not behave the way our model says it should. That is the starting point for the next revolution. Within a decade, Many of the current tensions will either resolve or harden into confirmed discoveries of new physics. Either outcome will be among the most significant events in the history of science. The standard cosmological model is not going to be thrown away. It cannot be. Its successes are too real, its predictions too precise, its explanatory scope too vast. Whatever replaces or extends, it will need to reproduce everything. Lambda CDM gets right. The microwave background spectrum, the acoustic oscillation scale, the large-scale galaxy distribution, the light element abundances, the accelerating expansion, while also explaining what Lambda CDM gets wrong. That is an extraordinarily demanding constraint, and it is exactly the right kind of constraint. Science advances not by abandoning successful frameworks, but by understanding precisely where they break and constructing more complete theories that explain both the success and the failure. The notes are not disappearing, they are compiling, and what they say, collectively, is not that physics is broken. Physics is working exactly as it should. The model makes predictions. The predictions are tested. The tests reveal where the model fails. Now the harder part begins, constructing whatever comes next. The universe does not behave the way we said it should. That is not a defeat, that is an invitation, and the scientists who answer it will reshape everything we think we know about space, time, matter, and the fate of everything that exists.